Length scales for interactions in magnetic systems cover a very wide range. We've already talked about the exchange interaction, which embodies the need to keep many particle wave functions antisymmetric, including the spin component of the electron, under exchange of particles. This interaction can be thought of as operating predominantly on atomic scales, and it's the details of the local interaction that drive whether a particular material is a ferromagnet or an antiferromagnet or a host of other possibilities. More complex are the dipole interactions that come about in a ferromagnet when local spins are aligned because of the exchange interaction. The dipole energy associated with this alignment grows in proportion to the volume of the magnetized region. Since this costs a macroscopic energy, ferromagnets that have not been magnetized, i.e. are not in some external magnetic field, have a tendency to form domains in which the macroscopic dipole moments are aligned in opposite directions in order to lead to an overall zero magnetization. This comes at a cost, however, because if you examine the walls between adjacent domains, one has to take a system in which the spins are aligned like this, and then in a neighboring domain like this, and therefore there is some region in which the local spins have to flip. And so there is a surface energy proportional to the size of the surface area of the domains, and the final domain size is set by an energy balance between the volume dipole energy and the surface energy associated with the formation of domains. Finally, there is an anisotropy energy. Net magnetization is easier to achieve along certain directions, either because of the intrinsic asymmetry of a crystalline material, or even simply because of the shape of the material. It is factors like that that lead to the hysteresis that allow ferromagnets to maintain a permanent magnetic moment. In addition, small particles have some intrinsically different properties from large particles. This plot on the left here in panel A shows the magnetic moment of a ferromagnetic atom as a function of cluster size. And you can see that in small clusters it is substantially above the bulk magnetization per particle shown by this dashed line here. A second feature of small particles is that even if they are ferromagnetic and therefore there is an exchange interaction driving an alignment, when they are small enough, their magnetization is flipped easily at finite thermal energy, with the result that they do not appear to be permanently magnetized, but they act rather as a paramagnet, the net alignment of a collection of particles growing linearly with the external field. So here's the magnetization versus applied field. It looks like a paramagnet. But as the particle size increases, the particles become closer to their true ferromagnetic cells and show the usual rapid magnetization followed by saturation as the entire sample is permanently magnetized. Superparamagnetism has a large number of applications, particularly in chemistry, where it is used as a way of separating desired products in a reaction. Recalling equation 435 from chapter 4, a particle with a magnetic dipole moment mz in a field gradient will experience a force in the z direction. In the case of a superparamagnetic particle, the dipole moment itself is induced by the absolute value of the field at that point. So the presence of a field polarizes the particles. The field gradient then attracts the particles to some point. So typically, if one takes, say, a pointed magnetic material, so the field gradient is very high at the end of this point, superparamagnetic particles will be attracted to it. So the picture here shows a cell sorting device in which stripes of a ferromagnetic material have been printed to generate a very high local anisotropy in the field. And the result is that cells targeted with an antibody attached to a superparamagnetic particle are deflected by this system of magnets to be collected at a different point in the microfluidic devices, whereas non-tagged cells flow through undeflected. A beautiful example of a nanostructured magnetic device is the giant magnetoresistance reading head that all of you almost certainly have in the hard drives of your computers. These devices rely on the fact that if you take a magnetic material and sandwich it between two layers of conductor, and so let us show the magnetic field in the magnetic material this way, when a current of electrons passes through the sandwich in this direction, electrons of one spin are scattered, so let's say in this case spin up, whereas electrons of the opposite spin are not. The way these devices work is as follows. They rely on a soft magnetic material, i.e. one that is easily polarized by the magnetic bits on the hard drive underneath the reading head. So let's say that the polarization on the reading head is this way. The polarization in the soft magnetic material will be the same. So now let's put our thin slab of electronic conductor here, and up here a hard magnetic material that let's say is polarized in this direction. And then let's put a contact down here. The polarization in both sets of magnetic material is the same in this case, and therefore for a current passing through this way, only one spin of electron will be scattered. If, on the other hand, the soft magnetic material at the bottom encounters a magnetic bit with the polarization reversed, like this, then in this arrangement, both signs of spin are scattered, and the resistance of the device is higher. This device is capable of reading very tiny magnetic bits very rapidly.